Hello, my name is Lakshmi Ravi and I'm a fourth-year PhD student at SiC-based. My advisors are Dr. Orlando Burgess and Dr. Dong Dong. Today, I will be presenting our recent work on the electrical insulation design and qualification of a silicon carbide-based generator-rectifier unit, or GRU, for high-altitude operation. This is the outline for my presentation. Let's start with the introduction. The conventional aircraft consists primarily of pneumatic and hydraulic systems. The rapid growth in the air transport sector and the subsequent enforcement of aggressive emissions targets have driven top aircraft manufacturers to push towards what is being called as the more electric aircraft, or MEA architecture. The advances in power electronics technology have enabled this evolutionary trend, wherein each successive generation of aircraft has employed more electrical equipment in place of hydraulic or pneumatic systems to enhance its operational efficiency. The MEA platform is also seen as a technological springboard for future all-electric aircrafts. This chart here shows that there have been consistent upward trends in the electrification of aircraft systems. Accordingly, as we can see here, there is an increase in the power demand to accommodate the increase in electrical loads. This also means increasing the voltage levels in the system in order to support the power requirements. The goal of this work is to design a safe and reliable generator-rectifier unit, or GRU, to provide a DC supply bus for the aircraft electrical system. The GRU design is expected to guarantee zero partial discharge operation under normal conditions while meeting the strict weight and volume targets. So to sum up, the combination of higher voltage levels, high power density, and the low pressure environment associated with aircraft cruising altitudes can result in insulation design challenges for the GRU. Before moving ahead, let's look at the GRU in more detail. Here is a schematic of the GRU system under consideration. The output DC supply voltage is 540 volts, that is, plus or minus 270 volts with respect to chassis ground. The maximum cruising altitude is 15,240 meters, or 50,000 feet, and the targeted power density is greater than 5 kilowatt per liter. The main system components are the GE silicon carbide power modules, their gate drivers, the DC bus, and the DC common mode choke. Next, let's answer the question, what is partial discharge? Partial discharge, or PD, is defined by the IEC as a localized electrical discharge that only partially bridges the insulation between conductors, occurring mainly due to the electric field stress concentrations in the insulation. It is influenced by the spacing between the conductors, their geometry, and the imperfections in the insulation materials. It can occur inside solid dielectric as shown here, or on the surface between two conductors as shown here, or around irregularities on a conductor as corona discharge as shown here. Prolonged partial discharges can result in insulation material degradation and eventually lead to complete insulation breakdown, which will then render the system inoperable. Therefore, as mentioned earlier, the GRU design must ensure zero PD under normal operation conditions. Next, let's understand the influence of air pressure on the breakdown electric field strength of air and the challenges associated with that. Paschen's curves provide empirical data about the breakdown voltage of air for homogeneous electric fields. This figure here shows that the breakdown field strength of air varies according to the product of the conductor gap distance and the atmospheric pressure. There are two key takeaways. One, for a fixed gap distance, lower air pressures result in lower breakdown voltages. And two, no breakdown is possible in an air gap when a voltage of less than 327 volts is applied to it. Therefore, careful design and surface E-field management is required to prevent discharges or breakdown in the 540 volt GRU system under consideration for successful operation at 15,240 meters or 11.6 kilopascal air pressure. In the next section, we'll look at the detailed insulation design of the GRU. The standard design practice for conductor clearance selection is to follow recommendations in relevant certification standards. For the GRU design, the IEC 61800-5-1 provides safety requirements including clearance distances for operating altitudes up to 2,000 meters, and the IEC 6664-1 provides an altitude correction factor or ACF, which is a recommended clearance multiplier for altitudes greater than 2,000 meters. An example calculation for the 570 volt peak GRU system is shown here. The required clearance at 2,000 meters is identified as 8 millimeters, and the ACF for 15,000 meters is identified as 6.67, which makes the required clearance at 15,000 meters for a 570 volt system to be 53.36 millimeters, which is quite high. Therefore, the suggested clearance multiplication factor can result in a design with very poor power density. Here I will introduce the proposed zero PD criterion, which is based on an inception E-field limit. As we know, practical systems include homogeneous and inhomogeneous electric fields. Therefore, we have to consider both cases in the design, and it is possible to derive an inception E-field based design limit using established PD models and data. For inhomogeneous fields, Niemeyer's generalized PD equation for arbitrary defects is used. This equation provides a relationship between defect geometry, ambient pressure, and ionization parameters of air on one side and inception E-field on the other. For homogeneous fields, the empirical formula for breakdown electric field derived from Paschen's curves is used. The combined inception E-field versus air pressure is plotted for different conductor geometries and spacings as the minimum of the calculated inception field and breakdown field for the two cases as explained earlier. The blue line shows the zero PD criterion for electric field value in air at 15,240 meters altitude, wherein it is proposed that the design must ensure that the surface electric field magnitude in the GRU will remain below this boundary through the application of surface E-field control techniques. The minimum point in this curve is 345 volts per millimeters. There are several solutions proposed in the literature to control the surface E-field on the converter level. The first group of solutions are material-based solutions. A common method is to use insulation potting to encapsulate the critical air gaps as shown in this example here, with silicone gel in this case for a high voltage transformer. The main drawback is the increased weight, which is not acceptable for aircraft applications. In the second example, conformal coating is used on the PCB to improve surface dielectric performance. However, it has limited effectiveness when it comes to surface E-field mitigation because the coating thickness is generally of the order of 150 to 200 microns. The next group of solutions are geometric solutions. These solutions can be easily implemented during the PCB design and are suitable for application in the GRU. The first example here shows corner correcting techniques to avoid field crowding around metallization edges. It shows that introducing a 1 millimeter fillet can lower the E-field magnitude by about 50% compared to a sharp corner. In the second example, field grading is achieved in internal layers of the PCB in order to mitigate both the internal and surface E-field magnitude by promoting uniform voltage distribution and increasing the field distribution area. In the third example, the busbar used in a single-turn inductor is coated with a conductive shielding layer and tied to the same potential as the core to mitigate E-field in the core window. And in the final example, customized PCB integrated shielding features are used to redistribute the electric field to mitigate peak field crowding in triple points along surface metallizations on the PCB. As mentioned earlier, these geometric solutions are easy to implement and can be easily adapted to suit the specific PCB assemblies used in the GRU, as we will see in the later slides. The high-level insulation design flowchart is shown here on the right. The first step is to identify the critical air gaps in the component and system assemblies. Next is to identify and enforce the inception E-field-based zero PD criterion for air at 15,240 meters. The GRU components and assemblies are analyzed using FEA simulations, where different E-field control techniques can be applied and adapted to satisfy the design limits. The initial design is then verified using a high-altitude partial discharge test. First, we start with the component level validation, and once that passes, we move to a full system validation. If either step fails, then we go back and modify the design. In the next few slides, let's briefly look at the GRU component level design details. For the gate driver, the 3 electrical nets are listed here. The critical areas are identified as the surface clearance between the pins of the digital isolator chip that is used in the gate circuit, and the air gap between the ground reference Rogowski coils embedded inside the gate driver PCB and the DC plus or minus module spacers, as can be seen here in this simplified 3D simulation model. So FEA simulation studies are used to finalize the design in these areas. PCB embedded shield plates or field control plates are introduced into the PCB underneath the digital isolator pads in order to bring the E-field magnitude in air to a value below 300 volts per millimeter, as shown here for the digital isolator. And FEA sweeps are conducted in order to determine the spacing between the Rogowski coils and the module spacers, labeled here as DBC and DBS. And the acceptable design region is identified from the simulation data and implemented in the final design. For the DC bus, a 6-layer heavy copper PCB with cavity connections is used. The layer stack used is shown here. Layers 2 and 5 are ground planes, and the internal layers 3 and 4 are assigned to DC plus and DC minus respectively. This helps contain the electric field on the surface and allows easier chassis integration. The net-to-net spacing and the dielectric thicknesses are chosen based on FEA simulations and applied to all the PCB apertures and the board edges. And the selected spacings are shown here. Between DC plus to DC minus, a 2 mm spacing is selected, and between the plus and minus DC planes and the midpoint, 1.5 mm spacing is selected. And here is an example 2D layer stack simulation, which shows that the electric field in air is below 300 volts per millimeter. For the DC common mode choke, the core window cross-section introduces several critical air gaps, as shown here, between the DC plus and DC minus windings, and between the windings and the grounded nanocrystalline core. Therefore, surface E-field management is necessary to address this issue. First, the assembly heights H1 and H2 are selected based on simulations as 3 mm and 2 mm respectively. Then, PCB integrated edge shielding features are applied to control the electric field in the lateral air gaps. The simulation plots are shown on the right, which show that the electric field in the lateral gaps without any shielding is very high. It's close to about 570 volts per millimeter. And on the right is the simulation plot with the edge shielding applied. And the shielding layer is connected to the same potential as the core, thus eliminating the voltage differential in the air gap and thus eliminating the problem. In the next section, let's look at the low pressure partial discharge testbed and the evaluation. Currently, none of the standards established for PD detection and measurement have addressed the ambient pressure condition. Therefore, the AC PD measuring test setup based on the IEC 60270 standard is modified to include a vacuum chamber for the DUT as shown here. The source is a 100 kilovolt AC power supply, coupling capacitor of 1 nanofarad, the CPL542 measuring impedance with 30 microfarad capacitor, and the MPD600 PD detector are used. The SiC-based PD testbed can achieve a noise floor of lower than 2 picocoulombs. The partial discharge inception voltage is defined as the excitation voltage at which repetitive PDs are first observed when the applied voltage is gradually increased from a low value at which no PD is observed. The PDIV acceptance criterion is chosen to be a value greater than 1.5 times the peak working voltage to allow safety margin in the design. The complete test procedure is as shown here. On this slide, let's look at the PD evaluation of the GE power modules. Power module insulation is typically measured between the terminals to base plates as per the IEC standard as shown here. However, it is insufficient for aircraft applications as it ignores weak electrical points between terminals under low pressure conditions. Therefore, a terminal-to-terminal PD test is the main focus on this slide. A special anti-series connection of modules is required to run a terminal-to-terminal AC PD test as shown here. It was found that the modules did not record any PD up to 1200 volts peak excitation at the targeted altitude as shown both in the table as well as the PD experimental waveforms here. This slide shows the PDIV summary for individual GRU components at different altitudes. At the targeted altitude at 11.6 kilopascal air pressure, all three components meet the acceptance criterion as shown here. Following successful verification of the component assemblies, the full GRU assembly with the chassis was subjected to a PD test. All high voltage nodes, that is the DC plus, minus, and AC nodes, were tied to high voltage potential, and the chassis was tied to ground potential for this test. The phase-resolved partial discharge pattern is shown here for 1 minute duration at the targeted altitude, and the recorded PDIV value was 579 peak, which is well above the working voltage of 270 volts. This validates the insulation design of the GRU and demonstrates zero PD performance at the targeted altitude. The final GRU assembly is shown here on this slide. The unit power density we achieved was 7 kilowatts per liter, which is greater than our target. And we were also able to verify zero PD operation at the targeted cruising altitude of 15,240 meters. The last section is a summary and conclusion. In summary, the installation, design, and qualification of a silicon carbide-based generator-rectifier unit were presented to demonstrate zero PD operation at 15,240 meters altitude. The breakdown electric field of air reduces with increasing altitudes, thus demanding surface electric field control techniques for this design. Inception electric field-based design constraint was proposed to limit the electric field in air to below 300 volts per millimeter, a value which was derived from the Paschen's curve's empirical formula for breakdown voltage and Niemeyer's model. FEA simulations were used to aid in the design of the main GRU components, that is, the gate driver, the DC bus, and the DC common mode choke. A high-altitude PD testbed was designed for GRU insulation qualification, and the acceptance criterion was set to PDIV of values greater than 1.5 times the working voltage for safety margin. The experimental results showed that the PDIV at 11.6 kilopascal meets the acceptance criterion. Thank you so much for your attention, and I'm happy to take any questions at this time.